So let me tell you what this class is about. We always start with the boring stuff first. I don't know why. Okay, but this is really exciting class. So, what is this class about? It's kind of four pieces, okay? And I'll tell you the four pieces. You don't need to get this down, but if you want to, terrific. It's kind of broken into four parts. The first part is you can kind of think of it as pre-calc in 3D. Second part is Calc 1 in 3D. Third part is, can you guess it? It's Calc 2 in 3D. And then the fourth part is actually where we get to do some results. We see what the fundamental theorem of calculus looks like in multivariate, as well as some applications. These are mostly in the physics world, but some really cool stuff. So these kind of four themes, or four different kind of units in this course, have different parts of them that build on each other. So first we look at pre-calc in 3D. What does that mean? Well, we're not going to look at limits yet. We're not going to look at any calculus. We're going to look at, kind of geometry. We're going to look at something called vectors, which, probably a lot of you have at least heard of before, if not already played with extensively. But we're going to do a complete introduction to vectors. We're going to look at, the coordinate system in this new space with an added dimension. And then also, different ways to even orient ourselves within 3D, right? So instead of just, X and Y and then adding a Z component and thinking of ourselves in like this boxed in unit system, what if we thought about it points instead of at the edge of a box, instead of being at the edge of a sphere or on the edge of a cylinder, right? So there's actually different coordinate systems that we'll use because they make integrating so much easier when you use them for certain types of problems. We'll look at things like the notion of curviness or curvature. What does it mean to be curved? How curvy is something compared to something else? So, and then we'll look at, surfaces and areas. In the same way that you saw area in calculus generalized to, accumulation problems, we're going to see these things happen, but not just in the 2D world, in the 3D world, right? So you can think of things with some depth to them, things with some height to them. So once we kind of orient ourselves with, and really this is going to be a study of vector and vector arithmetic. We're going to kind of build a new arithmetic on which we can do calculus. Once we do that, we're going to learn how to differentiate, right? Or take derivatives. And so, what does a derivative look like in 3D? It made sense when it was the slope of the tangent line, right, on just a flat sheet of paper. But now we're talking about in space, right? So I can move back and forth, up and down. I'm talking about steepness, right, as the derivative, rate of change. How do you talk about steepness when you're in 3D, right? If I'm on a hill, it could be steeper on this side of the hill versus this side of the hill. So I'm going to break this into the idea of what we call partial derivatives. Derivatives. Where we start to break it into the x direction and the y direction, or even in a, right, how do I measure the rate of change in a given direction, right? Let's say I'm looking down the hill this way. I'm looking down the surface at this angle. What's my rate of change? How fast am I changing at an instant down this trajectory? So it kind of scales up the amount that we need to consider when we up the number of dimensions, and not just by one, right? The complexity actually kind of pillows out, which is awesome. So we look at the notion of derivatives, partial derivatives. and then optimization. And the tangent line approximation, right, becomes the tangent plane approximation. So instead of thinking about a line intersecting a curve and it doing a very good job of approximating what the curve's doing at a given instant, instead, if we have some surface, we're going to use a plane to say, well, I'd rather deal with this linear equation of a plane instead of whatever this surface might be. And they can be pretty complicated in terms of their formula. So all sorts of techniques from Calc 1, we're going to find their analog in Calc 3. And I say this in 3D, this is kind of a misnomer. I really want to say in higher dimensions, because we are going to generalize a lot into, hey, this works for 3D, but that's just the stuff we can visualize. The math holds up when we scale up the number of dimensions to n dimensions, okay, for a lot of what we do. There's a lot of particulars to Calc 3 as well, or to R3 as well, right, meaning the three-dimensional space. But it goes beyond that. Our third unit's going to be Calc 2 in higher dimensions. What did we do in Calc 2? Integration, right? So what does integration look like if we're now talking about a surface instead of a curve? Well, instead of areas, right, they move into volumes, right? Instead of looking at under a curve, how much area can we get by slicing this thing up infinitely and adding up all those rectangles? Now we're going to be talking about pillars under a hill, right, to use an analogy there. So how do we do that? Well, we break it up in the X and Y direction, or we might come up with a custom direction. And we stack these little towers and add all those up, right? But this comes down to needing to actually integrate twice. So we'll be doing double integration. And we'll actually even look into triple integration when we're looking at things like flux or mass given a density, right, per unit volume. We're going to want to integrate 3 times to kind of make up for those 3 dimensions of length, width, height, and then maybe density per unit volume, things like this. So pretty cool stuff. Obviously, you're going to have to review and be pretty familiar with integration techniques from Calc 2, differentiation techniques from Calc 1. We're going to review them briefly as we go through. I'll throw a couple examples at you, but probably going to be wise to pull out the old notes, maybe even go through some old homework problems when you notice that we're in a unit from back in the day, right? Or we're using a lot of sines and cosines. Maybe I'll go review, that unit from Calc 1. And then lastly, we're going to be looking at the generalization of the fundamental theorem of calculus, right? What does it mean that we can slice things up and then add them all back up and tell us something about this structure and have that happen in multiple dimensions, right? Not to just have that be area under a curve to tell me the relationship between the rate of change and the total change. But what does that mean when we're talking about maybe a closed surface, right? How does that play? And what are the applications of that? And we'll see some pretty cool stuff at the end of the course. Again, a lot of it is rooted in physics. That's like at the boundary of my experience. I went for pure mathematics, which has no application in mind whatsoever. Okay, so I was totally theory based. So once we left pre-calc, we didn't see numbers again. I've heard it said that pure math is closer to philosophy than it is accounting. Okay, so it's very out there in outer space. So the physics stuff, I'm going to need the engineers to kind of inform me a little bit on if I'm steering you wrong or if you've have a cool application that I haven't heard of before. But obviously, those big results at the end are pretty well known and explored. So that's kind of the 4 units in the nutshell. We're going to do pre-calc in multivariate, calc 1, then calc 2, then put it all together at the end and try to do some really cool stuff. All right. So We're going to start today with the pre-calculus stuff, looking at our coordinate system. What are the analogs for curves in this space? Look at some equations of things and kind of get our feet wet in that way. It can be a little disorienting for most students at first to shift into 3D mode because you've been in 2D mode for so long. All right, but just to take your time with it. Every night you're hitting the stuff, you might take 1, maybe 2 nights off a week from this course, but probably no more than that, okay? I highly stress frequency of quality time over, I'm going to save this all for Monday night and try to do 6 hours of it, right? It doesn't really pan out. Maybe for some classes, definitely not for calculus. So titrate it and hit this every day so that it becomes familiar. There's another quote. I'm not going to drop too many quotes on you guys, but John von Neumann, who's arguably one of the greatest mathematicians in the last 100 years, said, nobody actually understands math. We just get used to it, which I think you could spend an entire week unpacking that quote. But just to say, do some work in getting used to it, because understanding it is a fool's errand. So a couple things too that I wanted to go over. This housekeeping piece. Actually, we'll do that at the end. Yeah. We'll do that at the end. All right. I'll show you a Blackboard and all that at the end as well. We'll just jump into this stuff. So if you guys want to pull out your note-taking materials, if you haven't already, we'll take some notes. I will try to post these notes as a PDF as well, but again, you're going to have access to the video, so I'm going to prioritize that, and if I can do the PDF easily, I'll certainly get to that. So we're going to look at R3, some basic surfaces, and the notion of distance in R3. So let's go ahead and recall what our old pal R2 looked like. And if this looks unfamiliar, we should probably talk after class and make sure that you're in the right spot. Haha, Melly, you're so funny. Okay. So have some point P prime with coordinates A, B. What does this look like in 3D? Well, what 3D is it's an extension of R2. Or another way you could think about it is that R2 is really embedded inside of R3, right? You've really been in R3 this whole time, you just didn't know it, okay? So on this piece of paper that's in front of you with positive y emanating out from you, positive x going to your right, that there's actually an up and down, right, on that space. And that's what we call the z-axis. Okay, the z-axis is up and down. And so how we typically draw this in the canonical position is this way, and this is how I'm going to draw it almost every time. And I'm cheating because I have this little snap grid thing, so that's why my lines are always going to be sharp, but nothing else will make sense. So what does this look like here? X, Y are on the ground, right? They're on the desk. Your z-axis is up and down. So that point, P prime, is like living out here, whereas I've come out a distance of A on the x-axis. I've come out a distance of B on the y-axis. And here I am with this point again, A, comma, B, comma, 0. Where 0 is my z-coordinate. You can think of this loosely as height. Right? So this lives in the what we call the xy plane, because it's like this sheet of paper. It's like your desk. But there is now this added dimension of z. We can add height to these points, project up and down. So what we used to call R2 is over here, and this was the set of pairs x, y like this, where x and y are both real numbers. It's a set of ordered pairs that were like this, right? And A, B is in this set. And then over here, we call this R3. And what this is, it's the set of triplets, x, y, z, where x, y, and z are all in the real numbers. This symbol here means in or is a member of. Just in case you haven't seen that notation before, I'll move my head out of the way. Is a member of. So set of triples where x, y, and z are all real numbers. Okay, so that means you can go right over and out wherever, A and B are real numbers, and then now up and down as well. So usually when I'm in the classroom, what I'll do is I'll make a corner of the classroom be the origin. Okay, so where is the origin? Origin's right here. That's a hard green to see. Origin's right here at 0, 0, 0. And so it can be helpful to kind of visualize this as the room that you're in, and that the origin is at a corner, right? So if you're looking at a wall right now, the origin's at where the floor meets the walls, and that lower left corner. Okay, so then your positive y direction is moving your head up to the ceiling. Positive x is moving to your left. Positive y is moving to the right. Okay, does that make sense? So you orient yourself with that as your 0. So if you kind of start with just associating that part of your room as being the origin, that will help when you're mapping back from sketching graphs to, that physical space in your room. Okay. If you're not always in the same room, you'll probably learn it faster because you got to map it to a bunch of different rooms. Okay. But try to draw yourself that mental image. In the text, there's kind of like a helpful little picture where there's like a window on this side. There's like a table with a little plant over here to let you think of this as being a room. All right, but it's how far over, and up and down. Okay. So this is what R3 is. It's the set of all triplets with x, y, and z all being real numbers. So some things that shift. The notion of quadrants. What are those going to become in R3? Well, quadrants split us up into 4, right? When we add that third dimension, this becomes octants, right? Think about splitting up and down now. What happens when we add that third dimension is you're going to split it up into 8 pieces. And drawing this is kind of a bummer. But I'll show you a graph of somebody who used a computer to do it. That's way too in-depth. Here we go. Let me share that. Everybody see that? So octant 1, it's drawn a little bit differently. It's oriented a different direction than I drew it. Okay, you see how x is coming out this way, y positive direction is that way, and then z is up and down. So octant 1 is still like quadrant 1. Everything's positive, right? X and y are positive, z is positive. Then you kind of wrap around the plane above the xy, you wrap around the space above the xy plane, and that becomes you know, quadrant 1, 2, 3, 4, and then below is 5, 6, 7, 8. Okay, so I'll put this in the notes and give you guys some time to digest that. You don't necessarily have to memorize that, but it would be helpful to kind of know where you're at. But quadrant 1 is the ideal quadrant. Why? Everything's positive. Okay, X, Y, and Z are all positive. So there's 8 octants, obviously. Octant 1, X, Y, Z are all greater than 0. Okay, so let's look at an example to kind of highlight where we're at. So we'll plot some points here. And your friends will ask you, what did you do in class today? Well, we plotted points. I thought you were in Calc 3. Yeah, we're in Calc 3. We're plotting points today. Just getting used to the space. It really does take some getting used to. By show of hands, how many of us have played with this coordinate system before? Okay, good number of us. All right, good. So this will be a good review. So maybe you guys can help me out move through this a little bit. So 1, 2, 3, the point, right? How I read this is how far over in the X, how far over in the Y, and then how far up and down, right? So this is a length of 1 in the X direction. I come over a length of 2 in the Y direction, and this point right here is like on the in the XY plane. And then up 3. So I come up parallel with the Z axis to this point here, and this is a length of 3. Okay, so this is the point 1, 2, 3. So -2, 4, 5. Who can help me out with that one? And you can just like verbally describe what I should do. -2, 4, 5.
You should go backwards on the X.
Yep.
Like where we don't have it drawn.
Right.
So kind of like go backwards to kind of to your upper right.
Yes, to the upper right.
And then come out lower left on Y4 and then go up 5.
All right, so here's my -2, right? Extend back through the x-axis in the other direction. Up 4 in the y. Right, so that's like here, this is the 4. Here's the 2. And then up 5. From here. All right, so if we were to sketch this over, this is at a height of 5 on the z. So here's B. Does that make sense? So this is in the quadrant 2, right? X is negative, Y is positive, Z is positive. Did I say quadrant? What did I mean? How many we got now? 8, right? So it's an octant. So this is octant 2. The first one was an octant 1. Point C, 3, -2, 1. Can somebody else help me out?
Yeah, you would go 3 along the same direction as the x-axis,
Yep.
and then you'd go opposite uh, of your point -2 or opposite in the y direction, and
Right.
then up 1 z direction.
And up one in the C. So we're over here, right? And so, thank you. And so, yeah, this is point C, and it's 3, -2, 1. And what you can kind of think of this as, and I'm going to do a pretty shoddy job of drawing this, is you can think of this as being at the corner of a rectangular prism, right? Of a rectangular box. And that's going to be helpful for a number of ways. A, this is the rectangular coordinate system that we're playing with right now. Okay, so this is the logical next step up. Just like when you're playing in 2D, you could draw a rectangle, right, for X and Y. This is at the corner of this rectangular box. And so you can kind of think of a line emanating from the origin and shooting out to the corner of that box. Okay, that's going to be helpful to generalize our notion of distance, how far 2 points are away from each other now, right? We used to have the Pythagorean theorem. What the heck do we do now, right? So we'll talk about that after we plot these next ones. So you guys do D and E on your own right now, just to kind of test your knowledge. Then we'll confirm in like 2 minutes. Okay, so for point D, should be over 2 in the positive X, over 4 in the positive Y. Right, so kind of coming out from that corner 2, over 4 positive, and then down through the floor -5, right? So like in your room, you'd be in the floor below you, or if you're in the basement, you'd be underground, right? And again, you can think of it as being at the corner of this box. And this is actually an octant 5, so it's the one living directly below octant 1, right? Because they wrap around. And then the last one here was what? -2, -2, -2. So that's going backwards 2 in the x direction, backwards y by 2 units, and then down 2. All right, so it's down here. And what is that? What quadrant? Anybody wants to venture a guess?
Would it be 8? It's 8 octant, right?
It's not the 8th. The 8th is actually over here.
Oh, it's 7.
This one's back here. Yeah, and we'll chalk that up to, you know, I'm not the greatest artist in the world. But yeah, so it goes when we're in the basement, right, underneath the XY plane, it goes 5, 6, 7, 8. Right, if this is 1 on top. These are not actual fractions, right? Okay. Cool. So we got a little bit our feet under us when it comes to where points are. I do want to talk about, you know, what does it mean to have distance in this space? How do we measure that? But first, I want to talk a little bit about generalizing, okay, now not just points, but curves and shapes from 2D. How do these things look in 3D? Okay, so a quick note here. From R2 to R3, we had, right, the notion of a line.
I have a quick question.
Yeah, send it.
Are you not in an octant if your z coordinate is 0?
Are you not in an octant? So you're at the origin, right? So it's the same question as, is the origin in one of the quadrants in R2? And the answer is like yes and no, right? But you know, if you're on the, you know, if you're on the axes, you know, you're really kind of on the borderline. So we'd say you're on that boundary rather than in one of the octants. Yeah, it's a good question though. Yeah. But yeah, it's good. Good to know where we are. So yeah, if you're on, you know, if your z is 0, you're on the xy plane, right? So you could even say I'm in one of the quadrants more generally. But if you're at the origin, x, you know, x equals 0, y equals 0, z equals 0, you're just in that boundary point, right? Cool. So moving from R2 to R3, what happens when we add height to each of these things, right? I took a line from R2. Here's my axes, right? So some line L. What does this look like if I let the z variable vary? Right? If this was like, you know, y equals 4x plus 1. How does this look in R3? Well, in the same way that when a variable didn't show up in a linear equation, we just let it vary freely, right? Like the line y equals 2 says, let x be whatever you want, y is 2, right? So in the same way here, in my xyz plane, the equation y equals 4x plus 1 doesn't mention z. So what does that mean? That means z varies freely. It is free to be whatever value it wants to be. We still have the line y equals 4x plus 1, and it looks like, what, positively going up like this, something like that. So here's the line, but if z varies freely, what dimension is z? Well, that's up and down, right? So any coordinate up and down lives also in this equation, right? Makes this equation true. So that means that we really have this like sheet or this plane. Oops, that's not right. So we really have this plane where all the points on here have the quality of x, 4x plus 1 for the y coordinate, and then just any z point will work. So a line generalizes to a plane. Other things that we know and love. The parabola. Y equals x squared plus 1. What does this look like in R3? Well, same stuff is true. It's still a parabola, right? That was awful. Still parabola like this. Y equals x squared. But z varies freely. So any height is okay as long as your x and y are following this rule. So what's this thing going to look like? Anybody want to take a shot?
A curved plane?
Yeah, it looks like a curved plane. Kind of looks like a curtain, right? It has something like this. Everybody kind of see how that's like in the background there. It's like a curved sheet of paper. And these all have, if I were to slice it at any region, it would have a cross section of a parabola. Y equals x squared plus 1. Because any point on this thing has coordinates x, x squared plus 1, and then any z. Okay, so just kind of introduction to some of the basic shapes and things we remember from pre-calc, how they look in 3D, because eventually we're going to want to integrate on top of these things. So first we got to kind of shake their hand, right, figure out what's going on. But that's what is happening with a parabola if we let z vary freely. We don't always, right, but I'm just trying to show you what this equation would look like in 3D. Now, what we call this is a cylinder. And I'll show you why after the next example, maybe. We call that the parabolic cylinder. And let's say we remember the equation of this thing. What's the equation of this beast before us?
X squared plus y squared equals r.
Yes. And I gave you the r, and it is the unit circle 1. Exactly. So in the rectangular coordinate system, the unit circle, this is its equation. How would this look in R3? Where I let the height vary freely. We're still going to have a circle of radius 1 in the xy plane, but z varies freely, so it's going to become a cylinder. Right, something like this where z varies freely. So what a cylinder really means when we say that term in Calc 3, what we're talking about is something that has the same cross sections if you go in a certain direction. Okay, so if you slice it with a laser right down the middle in planes parallel to x and y, they're all going to look like that circle, right? X squared plus y squared equals 1. That's what I mean when I say a cylinder. Cross sections sit on top of each other. And I'm going to put that in quotes because it depends on which way you're oriented, right? You could have a cylinder lying on the x-axis, right? But as long as the cross sections are the same, it's a cylinder. Okay. So that's why this counts as a cylinder, like I was saying before. Okay. Questions so far? Okay. Awesome. So let's visualize some things. Let's try to figure out what these would look like and try to see it, in your mind's eye before you put pen to paper. Again, we just are trying to get familiar with this coordinate space. So we're going to play with a bunch of different things. So visualize these things in R2 and R3. So what does x equals 4 look like in R2? Who can remember that one?
Just be a vertical line.
That's a vertical line. Out here at 4. This is x equal 4. So what we have here is x is 4 and y varies freely, right? In R3, we have x equals 4. And what's this thing going to look like?
I would assume this is wall.
Yep, I heard a plane, and I heard another offering there too. I couldn't see who it was.
I said wall.
Yeah, like a wall or a plane. Exactly right. So a line, if we add the dimension and let that variable run free, yeah, that's going to happen. So we'll have the x equals 4, and y varies. And then z also varies, and so what we get is a sheet here. And this is parallel to what we call we haven't said this yet, what we call the YZ plane. So when we look at the blank kind of Cartesian R3 space here, if this is x, this is y, this is z, before is really kind of important to note, all right, we're in the xy plane when we're in R2, where x is, where y is, where our axes are. But now we've got more than one plane going on. If we want to orient ourselves, like Ryan said, in terms of the wall, right? Where's the wall? Where's the floor? It's helpful to remember these things. So over here, that this plane that you see on that leftern wall, this is called the XZ plane because we're dropping out the y, right? It's all the points where y equals 0 in R3. Over here, we'll do it in a different direction. This is the YZ plane. And this one here is the one that's been your friend for so long. the XY plane. Okay, so you got the floor, left wall, front wall. XZ plane, YZ plane, XY plane. Okay, so, some of these practice problems are going to ask how close or far away you are from one of these given planes. And maybe we'll practice with that too. But it's helpful to have that reference point because it's where one of the coordinates is 0, right? In the YZ plane, what coordinates are all 0? X coordinates, right? All the X values are 0 when you're living inside that front wall, right? Because you haven't come out at all from the wall and not through. So what I'd like you to do is with this as kind of your template here, do this for y equals 6 and z equals 1. What do these things look like in R2 and then R3 if they're parallel to a plane? Tell me which one that is. So I'll give you a minute or two to do that. How does y equals 6 look and z equals 1 look in R2 and R3? And then if you finish that one, oh, not that. Oops. So here's z equals 1, and here's y equals 6. Z equals 1 obviously doesn't live in the xy plane, so you wouldn't see it, right, in R2. There is no z. And so it's just going to be a plane of all the points xy that have a height of 1. So it's kind of like you took the XY plane and shifted it up by 1 vertical height, right? Put some stints under there, like stilts, right? Raise it up on a platform. And then y equals 6, obviously a horizontal line in R2. So that becomes a plane in the in R3. And what axis is this parallel to? XZ. Yeah, absolutely. So here's the XZ plane, right? It's parallel to that wall. So y equals 6, a plane z equals 1, a plane, the z equals 1 is parallel to what plane? XY. See some people mouthing, lip syncing it. Yeah. XY plane. Awesome. So how about this guy? Y squared plus z squared equals 4. What does that look like in R3? What does this look like? Anybody want to take a shot at what they think it is? You had to guess.
Circle?
Circle.
Like a sideways cylinder, right?
Sideways cylinder. Yeah, definitely a circle involved, right? But since it's 3D, it's going to be a cylinder, and it's sideways. And so, yeah, what does it run along? What's allowed
Goes
to?
along X.
Yeah. Why do you say that, Alex?
Because X isn't in the equation, so it's allowed to be moved freely.
Exactly. X varies freely here. Has no restrictions. This guy's my constraint. So it's really a circle on the YZ plane. Looks something like this, right? And it runs along the x-axis like this. All of its cross sections are circles, but if you slice them along the x-axis, right? Awesome. Questions on any of that? Okay, so translating again some of the basic curves from R2 to R3. So I have what should be a simple question, but it's actually kind of not trivial if you haven't worked in this space before. How far is it from the point 1, 2, 3 to P prime -4, 5, -1? So how do we measure distance? So it might be worth recalling distance in R2. So distance between 2 points P and P prime. How do we find the distance between 2 points in R2?
Pythagorean theorem.
Yeah, Pythagorean theorem. Take the difference of their x coordinates, add it to the difference of the y coordinates. Each of those differences are squared. All right. x2 minus x1 squared plus y2 minus y1 squared, all square rooted. That would tell you the distance. It's the hypotenuse, right? Between 2 points. So this is your y2 minus y1. Here's your x2 minus x1. So in R3, and there is a fun geometric chase here, which I wanted to do with you guys, but the proof's in the book, and if you want to show it to yourself why it's true, it's really worth your time, I think. But essentially what you do is you use two triangles, right? You get the triangle that shifts you over in the XY plane, and then the triangle that shifts you up in the Z direction, okay? And so that distance formula is pretty nice in that it is the square root of x2 minus x1 squared plus y2 minus y1 squared plus the distance in the Z direction. And it really is a fun little proof that would take you 6 minutes to get through. So I do recommend it because I think it helps you wrap your head around things. But really, if these are at the corners of a box, take the Pythagorean theorem along the base and then across the diagonal of the box, if that makes sense, to get that corner to corner length. And so this is how we calculate distance, and it's pretty simple. So it's the square root of -4 minus 1 squared plus 5 minus 2 squared plus -1 minus 3 squared. And so what, that's 25 plus 9 plus 16, which is radical 50, which is what, 5 radical 2. Yes. So nothing really crazy. Sometimes it's as simple as tacking on the Z, right? Now you're in the third dimension. Distance formula, throw on the Z, there you are. The reason why is a little bit more nuanced, right? The proof behind it. Check that out. But sometimes it really is that easy. Other times we kind of pay a price for being in 3D because there's some peculiarities about having the third dimension, right? And not being an even number. And just the number 3 itself. But we'll see those couple as we go through. So that's how we calculate distance. It's nothing too astounding, but good to have in our back pocket, right? When we get into talking about vectors, for those engineers and a lot of us who have already taken physics, right, we know that a vector is really, it's got a magnitude and a direction, right? And the magnitude of a vector is what? If we drew it as an arrow.
Distance, right?
Yes, the length of the thing, right? The length from the base to the head. So the length is going to be important, right? To have the distance between a vector in 3 space, you need to know where it starts and where it ends. So we can compute that really easily. So you'll see when we're computing magnitudes of vectors, it looks very, very similar to something we just saw right here. Okay. It's also, don't be afraid to use what's called the quadrants. I don't know if they call it that in 3D, maybe just 2D. But to talk about the square of a distance too. Right, so that you don't have to take the square root. So you can just square it, say the quadrants is 50 instead of the distance being radical 50. All right. So some other stuff that you're going to want to know. Question. X squared plus y squared equals r squared. Versus x squared plus y squared plus z squared equals r squared. Here this is in R2. Here this is in R3. What are some similarities and differences that we'd expect here? Well, what is this guy here again?
The circle.
Yeah, this is a circle. And what is a
It's really just the points on the exterior of the circle, right?
correct? Yeah, circle of radius r, points at distance r from the origin. Right, or from the center. Here this is centered at the origin. So it's the shape that's formed by the points that have fixed distance. Right? And that's how we get that perfectly round shape. It's a fundamental shape. So that's the big takeaway here, is that it's the points at a fixed distance from 0, 0. How does that generalize into R3 if my distance now has a z component to it? It swivels around.
Should give us the surface of a sphere, but not its interior.
Right. Should give us the surfaces of a sphere, but not the inside. Right. So exactly right. This gives us the sphere in R3. This has radius r, and its set of all points x, y, z that are r away from the origin. And so it really is just the boundary. We call, I might say, note, inside it is called the ball. So we have the sphere, that's the outside, and then the ball is all the points inside, which we would describe with inequalities instead of an equation, right? Because these are all at that fixed distance. So that's exactly right. A sphere in R3 of radius r, all the points of a fixed distance. So let's sketch what that looks like. All right, so it comes out a distance of 4 on the x, 4 on the y, and 4 on the z, and then also, right, -4 in each of those. So a nice way to draw a sphere would be something like this. Mally, that's terrible. Please pass the pen to somebody who can draw. Okay. Looks something like this. I'm gonna cheat and just use my snap tool here. And so it hits at a distance of 4 out, and I'm going to move that in. So, and it is just the points on the boundary. So to talk about the points inside, like I said, you'd have to use inequalities. Questions on this before we scoot to like investigating the other space? Okay. So how would we use inequalities to describe the points inside the ball of radius 5 and outside the sphere of radius 2. So what does this thing look like? Well, it's a sphere of radius 5. Then we have this inner ball. Or I said ball, right? It's a ball of radius 5. And then we have this inner sphere of radius 2. And we're really talking about the points inside here. It's kind of like an avocado outside the pit, right? How do we describe that algebraically? Anybody want to take a shot at that? It is centered at the origin.
So I think what it would be
Mhm.
is 2 is would it be? Yeah. 2 is less than x squared plus y squared plus z squared is less than well, it would be 4 and 25, but yeah.
Right. Great. So we have the set of all points that are greater than this, right? 2 squared and less than 5 squared. Now, I wasn't super clear on, what's included and what's not. I think as read, it does not include those boundary points. But the point of this wasn't to split hairs over inclusiveness, just that we can describe this region using inequalities. Okay, so any point that's in this yellow space is going to satisfy this with its coordinates. Does that make sense? Okay, so again, playing with these different things and how they scale up to 3D, ideas that we've had before, inequalities, different regions. Now it's like a 3D space that you can put your finger on, which is cool. And I had a lot of examples I wanted to get to. Now I got to choose my favorite one. So let's do this. I'm gonna ask you to explore an idea here. What happens if I've got this sphere What happens when this intersects with the plane x equals 1? So what do you think happens? And then how do you show what's happening with algebra?
You get like a flat donut, right?
Flat donut. That sounds like a bummer. And you are close. Yeah, it is a circle. So it's a donut of infinitely thin material, right? Because it is just the circle. But yes, I would take donut. So let's see what happens. I'm going to try to show you guys this this tool. So this is linked in Blackboard, and I'll take some time to explain the different parts of it. But for right now, I'm just gonna. Oops, I broke something already. implicit surface. X squared plus y squared equals 9. And we're going to go out to 4. Okay, so we'll see the ball here. And then I'm going to plug in what do we say? X equals 1, which we know is a plane. Why did that change? I don't know. And now you can't see what's happening. It's all right. I'll put it back in the original position. So the circle, when it hits, the sphere, when it hits the plane, we get a circle intersection. How does that look algebraically? What is, right, you get this boundary around here. You guys can see my cursor, right? You get this boundary where the two meet. Whoa, whoa, whoa. You get this boundary where the two meet. What is that curve? Do we have a name for that? What do you think? So we got this sphere of radius 3, right? And it hits x equals 1, so we got this plane slicing it like this.
It's still a circle, right?
Still a circle. It's not a sphere, right? A circle, but what I'm saying is, what is its name or what is its equation? Well, we know that the x value is fixed, right? What is the x value? Yeah, it's 1.
X is going to be 1, yeah.
Yeah, x is stuck to 1. So any point that lies on this curve, right? And I'm not, it auto-filled this. I'm really just looking at the curve itself, that boundary, is going to have an x value of 1. So it's going to live on both things, right? It's going to be on the boundary of the sphere and it's going to live inside that plane where x values all equal 1. So it's going to make both of these things true, which means I substitute this x value in, right? So this becomes 1 squared plus y squared plus z squared equals 9. And so the curve is really this y squared plus z squared equals 8, which is what? It's a circle of radius radical 8, or 2 radical 2. And it lives out what? A distance of 1 from the YZ plane. So from that front wall, from the YZ plane, it's this circle kind of floating in space. Centered at the origin, right? But parallel to YZ. So you guys have attacked a good number of structures in R2 and R3. Some of these formulas are going to need to, kind of dust off a little bit, but that's fine. You've got the weekend to do so. I did want to show you where you can find extra resources in the class, as well as like your first assignment and stuff, and how the software all works. So I'm going to reserve some time to do that right now. And I also had a quick survey that I wanted you guys to fill out. So before we leave this, I want to say a couple things. First of all, I know this feels like a little, not even basic, because this can stretch your brain a little bit. But there's not a lot of application going on. We're gonna get to some of that, and again, some of this should just be fun in its own right. So I hope you're having a little bit of fun already. Just kind of checking out how things shift when we add a dimension, and also to say, don't get too tied to the graphs. I'm a very visual person, but at the same time, that can hold you back, because we're eventually going to leave behind 3 dimensions, and then graphs actually kind of hold you back. It's a place where the algebra holds up and the logic holds up, but the visualization breaks down. Right? So the second that you have 1 input and 3 outputs, now you're in a 4-dimensional space, and there's no surface that's going to mean anything to you. You can look at some cross sections and stuff, but it's going to start getting limiting pretty quick. So I'd rather have you think about dimensions as the number of things that you care about more than it is, right, X, Y, and Z, right? So a dimension is just something that you care about. It's a variable. It's a degree of freedom, right? Ask any sound engineer how many dimensions they play with on any given day. It's just one of those dials, okay? So that's really how I'd like to, in the back of your head, think about another dimension. It's just something else we're now keeping track of. So here it's now we can play in 3 space, and that's awesome. Moving forward, it's going to be time, space, and then, again, this generalizes to things that have lots of dimensions. And what have lots of dimensions, but things that are interesting in the world, right? So everything, every field has multiple dimensions that you want to care about. So that's why this class is cool. That's why we got to dip our feet into the water a little bit and just recall some of this basic stuff so we can jump into the really, really fun stuff later. So I hope you enjoy kind of orienting yourself in 3 space with the practice problems here. Any questions before we close out the lecture piece there?